All right, factoring, such a big part of our lives. Remember, we have talked about things like, remember this factoring flowchart? Maybe you don't, but the factoring flowchart can be very helpful to factor quadratics. We've also talked about difference of squares. We've also talked about the difference in sum of cubes. You can just go ahead and replay that video, pause on those things if you need to. Well, there's also other factoring techniques like factoring by grouping and quadratic form, and this is just going to run through all that stuff pretty quick. Well, the first thing we always want to do, no matter what we're trying to factor, is we always want to look for a common factor. And I notice right here, well, they all have an x. So I'm going to pull an x out to the front. I'm left with 8x squared minus 33x plus 4. Yeah. Now, what I have left over is still a quadratic. And this quadratic, well, we want to see if we can factor it. So I'm going to multiply 8 times 4. I'm going to look at my AC value, which is a positive 32. And I'm looking for two numbers that multiply to get positive 32, add to get that negative 33. Well, these two numbers are a negative 32 and a negative 1. These multiply to get me 32. These add to get a negative 33. And because I have 8x squared, I'm going to put 8x in the front of both sets of parentheses, and I still have my x out in front. Now the last step when we're doing this method, now there's other methods to do this problem, but when we're using this method, we want to reduce by as much as we can. This factor can be divided completely by 8, leaving us with x minus 4 right here, and this factor can't be reduced at all, so this is 8x minus 1. And so that is completely factored. Yeah. All right, we have x to the 6 minus 64. Well, this is going to use all kinds of different difference of squares, different sum of cubes. X to the 6 minus 64, this can be rewritten as x cubed squared minus 8 squared. We can rewrite this as a difference of squares. And so what's being squared here is x cubed, 8's being squared over here, so we can write this as x cubed minus 8 times x cubed plus 8. Now this is a difference of cubes, while this is a sum of cubes. We are cubing an x right here, we're cubing a 2 right there, and we can use our difference of cubes formula. So this is going to be x minus 2 times x squared plus 2x plus 4. Our signs are always same, opposite, always positive. This one right here is going to be, again, an x and a 2 both being cubed. And so this will be x plus 2 times x squared minus 2x plus 4. And the only thing difference in these are the signs. It's the same sign, the opposite sign, and always a positive sign. And so all this stuff is being multiplied together here, and we can't factor that anymore. Moving on up here, we have, look, one of those situations where it doesn't really look like what we've seen before. Maybe we have an x cubed here. I don't see any common factors, but notice we have 4 terms, which means we can try to factor by grouping. I'm going to group the first 2 terms and the last 2 terms and pull out what's in common. In common in the first 2 is x squared, leaving me with x plus 1. In common in the second 2 is a 5, leaving me with x plus 1. What's in common is a factor. And what's left on the outside, x squared and 5, is our other factor. We look at these to see if we can factor any more, and we can't, so we leave it the way it is. Here is our factored form. Finally, we've got this 3-term expression. We have an x to the 4th power. Well, because it has 3 terms, usually we can try to factor it like a quadratic. I can rewrite x to the 4th as being x squared squared. and I'm going to let u equal x squared. And I'm going to replace all of my x squareds with u's. Now this is a quadratic, and we can factor quadratics pretty easily. We know since our leading coefficient's a 1, we're looking for two numbers that multiply to get a -8, add to get a -7, and this would be a -8 and a +1. Well, of course, we don't actually have u's in our problem, we have x's. So I'm going to replace the u back with an x. We can look to see if we can factor any more, and we cannot. And so this is our factored form. We are completely factored. All right, we want to solve this. This is a quadratic because we have that degree 2. Now, whenever we want to solve any kind of polynomial, we want it to be equal to 0. So I'm going to add 9 to both sides. So we have 2r squared minus 4r plus 9 equals 0. Now, if a quadratic's factorable, that will save you a lot of time. I don't think this one is. So I'm going to use the quadratic formula. Well, quadratic formula, but we all know what that is. You don't need to see that. Now, in order to use the quadratic formula, we choose our a, b, and c, and we know it's -b plus or minus the square root of b squared minus 4ac all over 2a. We simplify. -4, of course, is a +4, plus or minus the square root of 16 minus 4 times 2 times 9. Well, 4 times 2 is 8 times 9 is 72 all over 4. Well, this is 4 plus or minus the square root of 16 minus 72. -56 all over 4. And so now we need to simplify that square root of -56. Well, of course, because we have the square root of a negative, we know this is going to have an I on the outside. And I'm going to think of the biggest perfect square that goes into 56. I believe it is 4. So this is the same thing as I times the square root of 4 times the square root of 14. And the square root of 4 is 2. So this is 2I root 14. So I'm going to replace the square root of -56 with 2I root 14. This is 4 plus or minus 2I root 14 over 4. And we can reduce this. We have all of our coefficients on the top, and our number on the bottom can all be divided by 2. So this is 2 plus or minus 1I root 14 over 2. And you can just leave it like that. Now, solving and dealing with polynomials that are not quadratics, well, we know it has as many complex zeros as the degree of the polynomial. So this one will have 5 complex zeros. To find the possible number of positive and negative real zeros, and even imaginary, we can use the Descartes rule of signs. We can look at the number of sign changes with f of positive x. Well, this sign changes once and twice, so we could have 2 positive real zeros, or it could go down by 2. We could have no positive real zeros. To find the possible negative real zeros, I can look at f of negative x, which is going to change the sign of all of the odd degree terms. So this, instead of being positive x to the 5th, would be a negative x to the 5th. Because this is an even degree term, this one stays the same. But because this is an odd degree, this is now a positive 25x. And of course, 75 is a constant. Constants don't change. So for my negative possible real zeros, the sign changes once, so we could have a possible 1 negative real zero. To find the possible imaginary, well, we can set up that chart. Our number of positives, our negatives, and our imaginaries. we know it's always going to total 5 for this polynomial. Well, I could have 2 positives and 1 negative, which would leave me with 2 imaginaries. I could have 0 positives and 1 negative, which would leave me with 4 imaginary, and that's all my combinations, so I could have 4 or I could have 2 imaginary zeros. Now, we have our possible rational zeros. Well, to find our possible rational zeros, our rational zero theorem says it's going to be the factors of our constant over the factors of our leading coefficient. So that would be all the factors of 75 over 1, which would just stay the same. So the factors of 75 could be positive and negative 1. They could be positive and negative 3 and 25. We've got 5 and 15, so this could be positive and negative 5, positive and negative 15, positive and negative 75. Can't think of anything else that goes into 75, so here are our possible rational zeros. Again, the factors of our constant over the factors of our leading coefficient. And finally, to actually find all the zeros, well, we want to solve this any way we can. I'm going to first try to solve this by factoring. Hopefully, we can solve this by factoring. So, I'm going to erase what I have here. And because we have 4 terms, I'm going to try to factor by grouping. In this first set, I can pull out x to the 4th power, leaves me with x minus 3. In the second set, I can pull out a negative 25, leaving me with x minus 3 once again. So when I factor by grouping, I have x to the 4th power minus 25 times x minus 3. Now I can factor this even more. This is a difference of squares. This is x squared minus 5 times x squared plus 5. And I still have x minus 3. And of course, because we are solving for our zeros, this is when our polynomial equals 0. And so we want to now use our zero product property. When we set x minus 3 equal to 0, that would solve to get us an x value of 3. We also want to set x squared minus 5 equal to 0 and x squared plus 5 equal to 0. This gives us x squared equals 5. And so x would equal positive and negative square root of 5. We also want to subtract 5 from both sides to get x squared equals negative 5, and x would come out to equal positive and negative I times the square root of 5. And so here are our other zeros. We have square root of 5, negative square root of 5, I square root of 5, and a negative I square root of 5. And we finish that problem.